In our last video on TinyML Micro Speech, we saw voice commands like on and off in action. We used a MEMS microphone with ESP32 to control a LED bulb and also went through the code, but that was pretty quick. So in this video, we are going to slow things down and focus completely on the code side, break it step by step and really try to understand how this example project works behind the scenes. Namaste and welcome back to Avinashee Tech. To be honest, the code here is a bit complex and involves some machine learning and audio processing concepts, but don't worry, I'll try to keep things as simple as possible. Let's dive into some engineering. I have the ESP project open here in VS Code, and for audio input, we are using ICS43434 MEMS microphone, which continuously listens to the sound and sends digital audio data to the ESP32 over the I2S interface. Now, let's start by getting familiar with the files in this project. First important file is audioprovider.cc. This file is responsible for capturing audio samples from the microphone and preparing an output audio buffer that will be later used for further processing. Once we have the audio buffer ready, next step is feature extraction. This part is handled inside the featureprovider.cc file and it internally uses another file called microfeaturesgenerator.cc where we actually run an FFT algorithm on the audio data and generate something known as a spectrogram. Now you can think of a spectrogram as an image, but instead of colors or objects, it represents audio frequencies that is changing over time. And this step is very important because we don't feed raw audio directly into the neural network. Obviously, the same word can produce very different waveforms depending on factors like speed, pitch, or even the speaker. So a spectrogram gives us a more consistent and structured representation of that audio. Once the spectrogram is ready, we pass it to our model and run inference using the interpreter. The model itself is already embedded in our project inside the model.cc file. After inference, we get output scores for different voice commands. These results are then processed by a recognizer object implemented in recognizecommands.cc, which decides whether a command is actually detected or not. And finally, based on the detected command, we take an action. This part is handled in commandresponder.cc. Now, the main functions.cc file is where we have a setup and loop kind of structure, similar to Arduino style. This is mainly done to make TensorFlow Lite Micro work in a familiar pattern, especially for embedded developers. Next, the micro model settings.h file contains all the important parameters related to the trained model. Let's open ESP32ICS43434.c file, and this is where everything actually begins in our project. Here we have the main application entry point, and inside this file, a task called tfmain is created. This task first calls the setup function and then runs an infinite loop where the loop function keeps getting executed. Apart from that, we also have some basic utility functions here like LED status indication and function to turn the LED on or off based on the detected voice command. Let's first jump into the setup function. This takes us into main functions.cc, but before we go any further, it's very important to clearly understand the model settings because everything in this pipeline depends on these values. Let's go step by step. First, the simplest one, audio sample rate. We are using 16 kHz, which means 16,000 audio samples per second. Next, we have feature duration, which is 30 milliseconds. This means we take a 30 millisecond chunk of audio and run FFT algorithm on it to generate one row of our spectrogram. Then comes stride duration, which is 20 milliseconds. So basically every new window starts 20 milliseconds after the previous one. Since our window is 30 millisecond long, this also means there is an overlap of 10 milliseconds between consecutive windows. Let's talk about feature size, which is 40. This number represents the columns in our spectrogram, basically the frequency components. After applying FFT algorithm, we initially get around 256 frequency buckets, and these are then grouped and averaged, which reduces them to a smaller number, around 40 meaningful features. This also helps keep the model lightweight and efficient. Next is feature count, which is 49, and this is the number of rows in our spectrogram. So we are essentially capturing 49 time slices of audio. If you multiply 49 by the stride duration of 20 millisecond, you get 980 millisecond, which is roughly 1 second of audio data being analyzed at a time. Then we have feature element count, which is simply rows multiplied by columns. 49 cross 40 gives us 1960 total elements in the spectrogram. Finally, max audio sample size, which is 512 samples. Let's quickly understand this. At 16 kHz, we get 16 samples per millisecond. So in 30 milliseconds, we ideally need 480 such samples. But FFT algorithms work best with sample sizes that are powers of 2, and the next power of 2 after 480 is 512. So instead of 480 samples, we take 512 samples, which actually corresponds to about 32 milliseconds of audio. So these are the core settings that define how our audio is sliced, processed, and fed into the model. I know that's a lot to take in, but hang on, we are just getting started. Now coming back to the setup function in main function.cc, first thing we do here is call the getModel method, where we pass our model data array, which is defined in model.cc. Right after that, there's an important compatibility check. Code verifies whether the model version matches the TF-Lite micro library version, just to make sure everything runs correctly. Next, we define the operations that our model will use. And now since we are working on an embedded system with limited memory, we don't include all the possible operations, only the ones actually required by this particular model. Obviously, the question arises, how do we know which operations are needed? And simplest way is what we did in our previous video, that is open the .tflite model in Netron and inspect it. In our case, we need 4 operations: reshape, convolutional 2D, fully connected, and a softmax. After that, we set up the interpreter. Here, we use something called a tensor arena, which we had declared earlier in an unnamed namespace. The size of it is 30 kilobytes. You can think of this as a dedicated memory block that holds all the input tensors, output tensors, and intermediate data required during inference. Once the interpreter is initialized, memory allocation for tensors is done. Then we perform a quick check on the input tensor dimensions, and since we are using a quantized model here, data type is int8. Moving ahead, we create a feature provider instance, and this takes in the feature size, which is 1960 in our case, and a buffer that will store the generated spectrogram data. Finally, we create a command recognizer instance, which will later help us decide whether a spoken command is actually detected or not. Now let's move to the loop function, which is right below the setup. This is where the real-time processing happens. First, we call populate feature data method on the feature provider instance. What this does is it continuously collects audio and converts all those small audio slices into features, basically building our spectrogram in real time. Once the feature buffer is ready, we copy this data into the input tensor of our model. The memory for this was already allocated earlier during setup. After that, we call the invoke function of the interpreter, and this is where the actual magic happens. The model takes in the spectrogram data and runs inference on it. Now in the original TensorFlow Lite micro implementation, after inference, there is a call to a method called process results from the recognizer, and this method averages the prediction results over multiple time frames before deciding the final command, which helps in making the output more stable. But in this ESP project, a simpler approach has been used. Instead of averaging over time, it directly looks at the output tensor at the moment, picks the class with the highest probability, and decides the command. This approach is lighter and uses fewer resources, which is great for embedded systems, but the trade-off is that the results can sometimes be a bit less stable. Quick recap. Audio from the mic comes into the ESP32 at 16 kHz. We take 30 millisecond chunks, run FFT, convert them into spectrogram slices with 40 features. Each slice is 20 milliseconds apart, and 49 such slices together give us about 1 second of audio data. This spectrogram is fed into our quantized model, inference runs, and we detect the command to trigger an action. Now, let's go inside the populate feature data method, and the first thing we see here is a sanity check. It verifies that the feature size matches expected feature element count of the spectrogram, and in our case that should be 1960. Next, we calculate something called the last step. Let's understand this with an example. Assume this is the first time we are entering the loop function. So the last time recorded would be 0 millisecond. Now let's say the current time is 100 millisecond. Using a stride duration of 20 millisecond, current step becomes 5. So effectively we now need 5 new slices of audio data. Now, since this is the first run, something important happens. We call initialize micro features. And here comes an interesting twist. Inside this function, we again call getModel, but this time not for our main command detection model. Instead, we load a second model, which is the audio preprocessor model. So yes, in this project, we are actually dealing with two models. One model for detecting voice commands like on and off, and another model for converting raw audio into a spectrogram. This second model might look quite complex if you open it up in Netron, and you will see operations like strided slice, RFFT, filter bank, and more. Just like before, we do a version compatibility check with TF-Lite library, and then we register all the required operators for this pre-processing model. Again, only the ones that are actually needed. A separate tensor arena is created here, this time of 16 kilobytes, since this model also needs memory for its computations. Tensors are allocated and initialization is complete. Coming back to populate feature data method, since this is the very first run, we want to build a fresh spectrogram. So slices needed becomes 49 and slices to keep from the old buffer becomes 0 and slices to drop from the old buffer becomes 49, which basically means we discard anything old and completely refill our feature buffer from scratch. Now, since slices needed is greater than 0, we enter a loop. In the first run, this loop effectively runs for all the 49 slices. Now this part is very important, so pay close attention. We have a variable called newSlice which starts from 0. Based on that, a new step value is calculated. For the initial slices, this new step is actually becomes negative. For example, when new slice is 0, calculated slice start time comes out to around minus 860 millisecond. So obviously, negative time doesn't make sense for audio capture. What happens? Inside the getAudioSamples method, start time is clamped to 0 millisecond for any negative value. What this means is for all those initial slices with negative timestamps, we are actually fetching the same audio starting from 0 millisecond. If you follow this through, you will notice something interesting. At new slice value of 43, calculated step becomes 0, so slice start time is finally 0 millisecond. After that, for the remaining slices, we start getting real progression. 20, 40, 60, 80, and finally 100 millisecond. So effectively, the first 43 slices of the spectrogram are redundant. They all contain data from 0 millisecond. Only the last few slices actually represent real-time progression of audio, and this is how we initially fill our 49 slice spectrogram buffer. Inside getAudioSamples method, we also pass a variable that will store how many audio samples were actually read along with the actual audio samples. Let's quickly go inside the function. If the audio system is not initialized, we first call init audio recording. Here, an audio capture buffer is created and a separate task is launched. This is the audio capture task. Inside this task, we configure I2S interface for the microphone and run an infinite loop where audio data is continuously read. At a time, we capture 100 millisecond of audio. Since our sampling rate is 16 kHz, that's 16 samples per millisecond, so for 100 millisecond we get around 1600 samples. These samples are written into the audio capture buffer and the timestamp is updated so we know exactly when this chunk of audio was recorded. Now, coming back to the getAudioSamples function, if you look at the code comments, you will notice values like 160 samples and 320 samples being used. Let's understand what that means. At a 16 kHz sampling rate, 160 samples correspond to 10 millisecond of audio. 320 samples correspond to 20 millisecond of audio. Now, remember our total window is 30 millisecond and we have a stride of 20 millisecond. So each new window overlaps the previous one by 10 millisecond. Because of this overlap, first 10 millisecond of the new output buffer is copied from a history buffer and this is the overlapping part. The remaining 20 millisecond is fresh audio data, which is read from the audio capture buffer. So effectively, each 30 millisecond window is built using 10 millisecond older data and 20 millisecond newer data. Once this new 30 millisecond buffer is ready, we then take its last 10 millisecond and store it back into the history buffer, so it can be again reused for the next window. This is how the overlapping window mechanism is efficiently implemented without rereading the same data again and again. Now going back to populate feature data, after collecting the audio data for each slice, we call generate features. This is where the FFT is applied on each 30 millisecond slice one by one. Using the pre-processing model, these slices are converted into spectrogram data with 40 frequency bins or columns and 49 time slices or rows. And that's how our final 2D spectrogram is generated, ready to be fed into the main model. Coming back to the loop function, we have already seen what happens once we have that full 1 second 2D spectrogram ready. From there, it goes into the model, inference runs, and we get our command detection. Now, let's quickly understand what happens when it's not the first run of populate feature data method. Say the last timestamp was 100 millisecond and the current time is 140 millisecond. With a stride of 20 millisecond, that means 2 new slices are needed. But this time, instead of rebuilding everything, we keep 47 slices from the previous spectrogram and drop the oldest 2 slices, so the total size still remains 49 slices. What happens internally is pretty efficient. Existing feature data is shifted in the buffer. Only the latest 2 slices are computed using new audio samples and everything else is reused. Rest of the process remains exactly the same. So yes, that was quite a deep dive into the code. I know it can be a bit overwhelming at first, but take your time. Maybe rewatch parts of it and it will start making sense step by step. If you found this helpful, don't forget to like, share and subscribe. It really helps support the channel and lets me keep making more such content. This is Avinashee Tech signing off.